Okay. All right. Can everyone see the slides, the title slide?
Yes.
Okay. Well, good morning, everyone. Welcome to the next installment here of EMI test methods. And today will be the lecture portion of CS114, conducted susceptibility bulk cable injection. And then we will follow up with the lab session on Wednesday. And here's a list of the topics that I'll be talking about today. The demonstration, of course, will be on Wednesday. I may hit at least some of these topics as time permits today, but then the demonstration proper will be on Wednesday. So, a couple words of introduction. CS114, conducted susceptibility bulk cable injection, is an extremely useful test method for evaluating susceptibility to induced currents and potentials on cables. I really like this test method. It really is indeed wonderfully useful. However, it has many nuances that are important to understand in order to implement it properly. So what I like to say is, I've even practiced this joke. So here you go. What I like to say is, I just can't say enough about CS114, but you're about to listen to me try. So there you go. That's my warm-up joke for you. You're welcome. So anyway, I'm going to talk about the textbook method in the mill standard, but I'm also going to talk about a simplified method that can be used in the development lab prior to bringing your test article to the EMI lab. That'll be mainly what I will demonstrate on Wednesday. I think it will still, at least my intention, it will still illustrate the basic principles of the test method, but also illustrate how you can do it in a simpler way, just in your development lab. Okay. So just by way of review, we'll go through this stuff fairly quickly, but these are same charts from the overview session, just underscoring the point that interconnecting cables are part of the equipment under test, and you can't shortchange them. You have to bring plate representative or we've got the spacecraft centric approach here, but flight representative means, representative of what you're going to have on the platform, right? And I just submit that there's no such thing as a box only level EMI test. It's box plus cables. And when you meet your radiated emissions and susceptibility requirements for electric field, that is RE102 and RS103 requirements on a military platform, there's generally very low risk of crosstalk. Because the default RE102 limit corresponds to common mode currents that are much lower than anything that's likely to pose a crosstalk risk. And so also, since Goddard platforms, I think many NASA platforms don't use antenna connected receivers below 200 megahertz, we generally follow the guidance in the mill standard itself that recommends you only apply RE102 in frequency ranges where you have antenna connected receivers. So we generally apply it only above 200 megahertz, and crosstalk is our dominant concern below 200 megahertz. Just a reminder that when the RE102 test method, the test antenna is placed 1 meter from the test setup boundary, and that is a non-negotiable. It has to do with the calibration factors for the antennas. We'll talk about that more in RE102. I think somebody has an open mic, by the way. Can you please mute unless you're asking a question? And so there is an antenna configuration break at 200 megahertz. So that's a handy place to just say, okay, well, we will apply RE102 above 200 megahertz and then implement common mode conducted emissions and susceptibility measurements below 200 megahertz. So again, this is all review, but just to set the stage here. And just, reminder about differential mode and common mode currents. Differential mode is, generally speaking, the intentional path, your intended return path for your current. And then common mode currents are, generally speaking, the ones that find some alternate path back to the source. beyond the one that you've intended. So common mode currents are, of course, mainly what we're talking about here. Again, CS114 is primarily about common mode conducted susceptibility, but as we'll also discuss, it's about injection on power leads. So we'll talk about both of those things. So recall from the common mode conducted emission session that the mutual inductance from a culprit cable to a nearby victim conductor will induce currents on it, so a bit like a transformer. And in the worst case, the victim current, the magnitude of the victim current can equal the magnitude of the culprit current. So that's the basis of how we're evaluating common mode conducted emissions and susceptibility. Okay. One of the a nice thing about doing these kind of measurements is that we use clamp-on current probes, so a clamp-on current monitor probe for common mode conducted emissions, and a clamp-on current injection probe for susceptibility, which is going to be the major thing we're going to be talking about in this session. As you see here, both of these probes they just clamp on. There's a clamp here. You open it up, and clamp it around the cable that you want to evaluate. And there are no disconnections or reconnections needed, no disruptions to your configuration. And measurements may be performed right in your development lab. And I always highly recommend you do these tests in your development lab before you bring your hardware to the EMI lab. So in addition to common mode, as I mentioned, we also use CS114 to evaluate compatibility with the power subsystem in the high frequency range. Just a review here of general power system architecture, kind of a cartoon high level. You have a bunch of loads hanging off of your common distribution point. All of them will generate some amount of differential mode conducted emissions. And all loads will see the combined noise potential at this distribution point. So the combined currents, the differential mode currents of all the loads multiplied by the common source impedance. So we define our conducted susceptibility limits to provide a worst case upper bound for the composite voltage ripple at the distribution point that everyone will see. So a benchmark at least that I've used on most of the platforms I've supported, we start with the total allowable voltage ripple at the distribution point of 1 volt peak to peak in the time domain. And then we very conservatively translate that to a level of, for frequency swept based conducted susceptibility tests, we'll apply 1 volt RMS over the frequency range of 30 hertz to 50 megahertz. So in the last session, we talked about CS101, which covers the lower frequency range, 30 hertz to 150 kilohertz. And then CS114, as we'll discuss in more detail a little bit later, that covers the higher frequency range, 150 kilohertz to 50 megahertz. And it replaces the old CS02 test method. And so we'll talk about that in a little bit later as well. So CS114, and this is right, chapter and verse from the mill standard. I do this as much as I can to just let you know that I'm not making things up. But the highlighted text there, the basic concept for CS114 is to simulate currents that will be developed on platform cabling from electromagnetic fields generated by antenna transmissions both on and off the platform. And the basic relationship for the limit level in the resonance or flat portion of the curve is 1.5 milliamps per volt per meter that is derived from worst case measurements on aircraft. And that's all chapter and verse from the mill standard. So in this flat part of these limit curves, and we'll get into this, trust me, we'll get into the physics of why these curves look the way they do. But in this flat part of the curve here, the relationship is defined as 1.5 milliamps per volt per meter. So the transfer function is expressed as a current per incident electric field. And that tells you, all this underscores that CS114 was developed specifically to simulate. You fix that. There we go. Real-time fixing. All caught on video too. But there we go. To simulate coupled currents resulting from incident electric fields below 200 megahertz. So it was specifically developed as a conducted equivalent of RS-103. And it also applies to cable-to-cable crosstalk. But we primarily relate it to RS-103. So whether coupling is from an incident plane wave or from cable-to-cable crosstalk, it all comes down to Faraday's law. You know, it's just the B field, the magnetic flux density that's penetrating a loop. The time rate of change of that total flux it will give you an EMF or an induced potential in that loop. And some recommended reading here, a lot of this was inspired by a paper that Ken Javor wrote for the so almost 30 years ago. So, you know, but physics has a way of remaining constant. So I have a copy of this paper. I believe it's on the Teams page. Let me know if you have trouble accessing it. But it's a really excellent paper that forms the basis of a good bit of how that's shaped my thinking of much of what you're going to see in this presentation. So so just continuing on this concept here, when to first order, when we look at a magnetic flux or magnetic flux density or B field penetrating this loop, again, whether it's from an incident electric field or cable-to-cable crosstalk, the first order, we're going to assume that B is constant over the height h. Okay. Now, for an electrically short cable, so when the length is much shorter than a wavelength, so at low frequencies, we can assume that B is also constant over the length L. So our total flux, the total magnetic flux, is simply the B multiplied by the area, which in this case is just the height times the length. And then the induced potential in the loop is just the time rate of change of that flux, which can also be written as 2 pi f times v times the flux. And so that increases with frequency. Okay. So when the frequency is low, when it's an electrically short cable, when L is much less than lambda, then the coupled potential is going to increase with frequency. Now when you get into a realm where the cable is electrically long, which generally speaking is, you know, one school of thought is when the length is more than 1/10 of a wavelength. Some more conservative schools of thought say maybe 1/20th of a wavelength. But on that order, when L is greater than 1/10 of a wavelength, now the B field, the B vector, is going to vary over the length L. We're still going to assume that it's constant over the height, but it's going to vary over the length. You know, if our incident wave is coming in from this direction, okay, now it's going to vary sinusoidally along the length. And also, if it's cable-to-cable crosstalk, the B field to first order is going to follow the contour of the current along the length. And so, again, when a cable is electrically long, that means that the current and the voltage distribution is not constant over the length. It's going to have some sinusoidal, well, every frequency component is going to have some sinusoidal variation along the L direction or the Z direction here that I've defined it. So the total magnetic flux now you have to integrate over the length. We're saying it's constant over h, so we can just pull the h out of the integral, but then it's just the integral of B of z from 0 to L. All right. So now, just looking at this more intuitively, sparing you the math to some degree, if we increase our frequency to the point where, like what's shown in the diagram here, where the length is exactly 1/2 of a wavelength, we'll look at this snapshot in time where the B field has this distribution over the length of the wire, over the length of the cable. Okay, so you're getting exactly half of a cycle over the length of the cable. This will give you your maximum flux. Okay. You can't get any more than this, because when you keep increasing the frequency, right, you're going to get some cancellation. You're going to get some of the negative part of that distribution along the length of the cable. So when you increase the frequency to the point where the length is now a full wavelength, now you have complete cancellation. You have just as much flux going in this direction as you have going in this direction. So the net flux is zero. Okay. And that's going to be true whenever the length is an integer multiple of lambda. Okay, so basically this right column, we just say that the total net flux is going to be zero for all of these cases where L is some integer multiple of the wavelength. So if we come back over here, let's start where L equals lambda and then increase the frequency to the point where the length is now 1.5 wavelengths. Well, you're going to get a full cycle here over the first 2/3 of the length. That's going to give you cancellation. So the net flux from these contributions is going to be zero. Now you have this, the net flux is just from this contribution over 1/3 of the length. Okay. So you could work through the math, and I have, because of course I have, but you can just look at this visually. You can see that the total flux, the net flux here in this case, for L equals 3 lambda over 2, is now going to be 1/3 of lambda max, of the maximum flux in this case. Okay, everybody with me? Okay, so then, we increase to 2 lambda and we get full cancellation, but we increase the frequency some more to now where the length is 2.5 wavelengths, 5 lambda over 2. And it's a similar case where we have 2 full cycles that provide full cancellation. And now the net flux is reduced to this section here, which is only 1/5 of the total length of the cable. So now the total flux, the net flux here, is the maximum flux divided by 5. So we can see here that the net coupled flux decreases with frequency, right? And it's proportional. It's proportional to 1 over F. So when you increase the frequency by a factor of 3, you get 1/3 the coupled flux. Increase by a factor of 5, you get 1/5 of the coupled flux. Okay, but the coupled potential equals the time rate of change of the flux, or 2 pi F times the flux. So the coupled flux, or I'm sorry, excuse me, the coupled potential increases with frequency. So those two effects offset each other. So for a constant B field over frequency, that will give you a constant coupled potential envelope when L equals greater than lambda over 2. When L is more than 1/2 of a wavelength, the envelope of the coupled potential will be constant for a constant B field over frequency. Everybody clear? Everybody good with this? Because this is crucial for understanding everything that's coming up. Anybody? At least a sign that you're still there and not snoring.
Looks great. Thanks, John.
We're good.
Okay, good. And if you're snoring, please stay muted. But that was another one of those joke things. I'm on a roll. Is there I see a hand up. Is there somebody have a question?
No, I was trying to give you a laugh and I hit the wrong button.
Okay. All right. So if you are inclined to work through the math, I have the derivation in the backup slides that gives you this equation. And it might make your brain melt at first, but it well, like most mathematical things, at least to us mathicists, it makes a lot of sense. It is a sinusoid, or a sinusoidal distribution over frequency. So L over lambda, I've put things in terms of the fraction of a wavelength, L over lambda. Well, that's proportional to frequency. Okay, so 1 over lambda is proportional to frequency, right? Lambda is speed of propagation divided by frequency, or if it's air or vacuum, it's 300 divided by frequency in megahertz. But this, we'll get into specific frequencies, you know, coming up, but keeping this more generic, it really is in terms of the fraction of a wavelength here, but it is proportional to frequency. So this is effectively frequency on the horizontal axis here. So this just mathematically expresses what we walked through heuristically on the previous chart, and the derivation is in the backup slides. It basically comes, you know, you start with the B field and then do the integral and determine the total flux and then the time rate of change. And then, like most of this sort of thing, it's just substitutions. Like you know the relationships between B and H related through mu, and then H and the H field and E field are related through the wave impedance. And if it's a plane wave, it's the characteristic impedance of the medium, 125, blah 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 blah. You'll see that all that in the backup slides. And if anybody is interested and there's and time permits, we can walk through that at the end. But this is the equation you get: 2 times the height above the ground plane, and then sine of pi times the L over lambda. So if we just kind of look at this piecemeal, like I always like to look at simplifying cases that can help you make a bit more sense out of what looks like a complicated equation. So for one thing that helps is that for small theta, sine of theta in radians, that is, sine of theta approximately equals theta. So for you know, and for small theta, that's our sine argument. That means when L over lambda is very small. So when we're on this part of the curve here, we can just bring that argument out front. So I'm just rearranging terms a little bit here, but it's 2 pi times H times L over lambda. And so that increases linearly with frequency, or with L over lambda. And that's what we see here. So when L over lambda is, certainly when it's less than about 1/10 of a wavelength, the curve is quite linear, and it's increasing linearly with frequency. And then, just as we discussed on previous page, we have nulls when the length is an integer multiple of the wavelength. Then we have peaks when it's an odd multiple of a half wavelength. Okay. And so then we can simplify this to an envelope, which is what we can carry forward. If we take our linear expression here for this low frequency part of the curve, and this is our voltage as a function of incident electric field, okay, V over E naught. And so we have 2 pi H times L over lambda. And if we extend that line up to where L equals a half wavelength, L equals lambda over 2, and then we basically just take that value where L equals lambda over 2, and we just plug that into the equation here. So if that's L equals lambda over 2, that gives you 1/2 here in the parentheses, cancels out the 2, you're left with pi H. So we have a flat line of pi H for L greater than lambda over 2, L greater than a half a wavelength. Now it's clearly a little bit conservative here, right? This is a little bit higher than the actual peaks here, but for establishing a CS limit, a little bit conservative is not a bad thing, right? So that's just kind of the conventional way we have of doing this. Okay, but that gives us our envelope that we can carry forward for establishing how we want to test for conducted susceptibility. And for our H, as defined in the mill standard, meant to point that out. Go back to that initial figure here. The height of 5 centimeters is the height above the ground plane specified by mill standard 461G for our test cables. Okay, so that's where this 5 centimeters comes from. It's not something I just dreamed up. So using that, pi is pi, right? And you plug in 5 centimeters for H. you get about 150 millivolts per volt per meter for this flat part of the curve. And expressing it in dB, it's 104 dB microvolts per volt per meter. So we'll come back to this here presently. All right, so summarizing field-to-wire coupling, the incident magnetic flux, remember that it induces a potential. Sometimes we get a little lazy and sloppy and say magnetic coupling induces a current. And the current is a secondary effect. It induces a potential in a loop, in this case, your wire above ground loop, per Faraday's law, where the induced potential is the time rate of change of the incident flux. And per Lenz's law, it's the negative sign, but we're mostly just dealing with magnitude here. So the induced current is determined by the impedance of the configuration. And that's going to be a recurring theme here. So for a shielded cable with the shields terminated to chassis at both ends, then when for the electrically short case, where in this case we'll say that's for L equals less than a half wavelength, the impedance is going to be dominated by the loop inductance. Okay, with the shield that's terminated to chassis at both ends, and from a resistive standpoint, ideally that's zero resistance. Now, obviously, we know there's no such thing, but very low resistance is what you want for a good shield to chassis or shield to back shell termination. You want that to be, less than 2.5 milliohm. So the impedance is going to be dominated by the loop inductance, and so for cable above ground, 5 centimeters above ground, that's going to be about a microhenry per meter. And the inductive reactance, of course, is proportional to frequency, J omega L. So that means your coupled potential and your inductive reactance are both proportional to frequency. They're both increasing linearly with frequency. So that means you will have a constant induced current over frequency for a constant incident field over frequency. So bear that in mind. That's another thing we're gonna keep coming back to. That's central to this test method. Then when the length is greater than half a wavelength, the impedance will plateau at the characteristic impedance of the wire above ground transmission line. That's generally about 300 ohms for a height above ground of 5 centimeters. And I have wire above ground transmission line parameters in the backup slides. So that covers the basics of field to wire coupling, just the physics of how potentials and currents are induced in cables from an incident field, whether that's an incident plane wave or cable to cable crosstalk. So now we have this test method, CS114, to directly simulate that coupling. And so any questions about the basic physics before we plunge into the test method?
No.
Well, let's get on with it. So this CS114 was developed specifically to simulate coupled currents from incident fields, as we've just talked about. It specifies that you put your probes within a total of 10 centimeters from the equipment under test to make sure that it's less than a tenth of a wavelength at the highest frequency of interest, which is 200 megahertz. With CS101, with low frequency test methods, you're dealing with very long wavelengths, like miles. So where you inject along a 1 or 2 meter cable doesn't matter. When you get into these higher frequency test methods, or at 200 megahertz, your wavelength is 1.5 meters. Well, to be less than a tenth of a wavelength from the equipment under test, that you need to be within 15 centimeters. So they conservatively say 5 centimeters from the UT to your monitor probe, another 5 centimeters to the injection probe. So these things are very important to pay attention to. They're there for a reason. So the center point of this test method is the injection probe. Okay, so it has a connector for a signal input. It's a coaxial connector, generally an end connector. Hearing a hot mic. Does somebody have a question? Okay, if your mic is hot, please mute unless you're asking a question. Okay, so you have an end connector where you apply signal input, and that's connected to a coil of wire that wraps around a magnetic core. Okay, then it induces a magnetic flux in that core. Somebody still has an open mic. Would you please mute? Okay, thank you. So then when you clamp the probe around your cable under test, that magnetic flux couples through the loop, and then that time varying magnetic flux induces an EMF or a potential in that loop, right? In this case, formed by the cable under test and the ground plane. Okay. And this clamp-on injection probe, again, reiterating that it requires no disconnections or power cycles. So you can go from one cable to the next without disconnecting or without cycling power. So it can make your most efficient use of test time when you can just move this cable to the different cables that you're move the injection probe to the different cables under test without cycling power or making any disconnection. So all injection or signal injection test methods generally require a pre-calibration step. Okay, and in this case, it's a pre-calibration into a 100 ohm test fixture. Now, first, I'm going to talk about the setup per mil standard 461F. I'm fully aware that I'm talking about F when most of the time I'm hitting you over the head saying that we should be working to G. So I'm making a point here. So I know full well that I'm looking at a previous version of the mil standard. But this is a simpler setup where you have a signal generator and an amplifier driving the injection probe, and it's going through a directional coupler here, which is, if I remember on Wednesday, I'll have some directional couplers out to show you if you haven't seen one. But it basically feeds the signal through, and then gives you some attenuated version of it. It'll tell you whether it's 20 dB down, 30 dB down, whatever it is, that you can tap off and go and measure it, take it to a measurement device. Okay. But the main thing is you're providing you have a signal generator and amplifier that's driving the injection probe, and then you have a 50 ohm dummy load on one end, and then the 50 ohm input of your measurement device on the other side. So that's what makes it a 100 ohm fixture. You have a pair of 50 ohm impedances on either end of this thing. And so the entire point of the pre-calibration step is that you're recording the forward power level required to establish the desired pre-calibration current at each frequency. And then that determines the drive level required to establish not to exceed levels, which is an open circuit potential and a short circuit current. Those are what I would call universal truths for any signal injection technique. You want to establish your maximum open circuit potential. What's the maximum potential you can drive into a high impedance? And what is the maximum current that you can drive into a short circuit or very low impedance? Those are your extremes. So if you establish safe levels for those two conditions, anything else is in between, and you're keeping your hardware safe. All right. So that's the pre-calibration step per mil standard 461F. Now in G, they in the appendix of mil standard 461G, they include this paragraph that I'm just going to go ahead and read this. Ideal bulk cable monitor probes would have no effect on the circuit under test. In reality, there is a transfer function associated with insertion into the calibration or test circuit, not to be confused with insertion loss. We will talk about insertion loss shortly. However, a well-engineered probe might introduce only a 1 dB response change after introduction into the 100 ohm calibration circuit. There are other problems that may be encountered when conducting a bulk cable test, e.g. loose or damaged connections and center pins, damaged cables, bad attenuators, and so on and so forth. In computer-controlled systems, it is possible to cross the two spectrum analyzers or use of the probe outside of an appropriate band without realizing it. Okay, the main point are these last two sentences. This will never be discovered while conducting the test. Therefore, revision G adds the monitoring probe to the calibration step, and a new verification step was added. So that's your context for the next slide. So in Mil Standard 461G, it's basically the same setup as what's specified in F, but they add the probe that you're going to use to monitor the current for the actual injection into the equipment under test. You put that into a calibration fixture with a coaxial load to simulate the load that the current probe itself is going to put into the circuit when you're doing the actual injection. Now, all that stuff on the previous slide said those effects in general should be minimal. And if it changes your reading by a dB, we're generally not looking for 1 dB problems here. We're looking for many dB problems. So by and large, it's probably not gonna change things very much. But to do things per the letter of the law, this is the recommended calibration setup for Mil Standard 461G. And then they do a verification step when they play back those pre-calibrated levels while monitoring while using the monitor probe to tell you what current are you actually seeing. So that's going into a measurement receiver. And so you verify that when you pre-calibrate, you play back those pre-calibrated power levels, that you're getting the current that you expect to get. Okay. So what is this calibration fixture? Well, it's a hunk of metal. And what it does is it has a pair of coaxial connectors on either side, generally speaking, N connectors, and it feeds the center conductor through the fixture, okay? And then the shield of the coaxial connector is tied to the base of the fixture. So here's a picture of one. This is one that I use in my lab all the time. And you can't see the feed through here, but the probe clamps around it. And on Wednesday, I'll show you this, show you this more explicitly with a real one in the lab, and then before I put the probe on. But the center conductor from each of the coaxes here feeds through, and you clamp the probe around it, and you're inducing, you apply your signal to the input, and you're inducing that magnetic flux through that loop. Now between the center conductor, the feed through, and the base of the fixture, you have your 50 ohm dummy load on one side, and then the other side goes to the 50 ohm input of your measurement device to provide the other 50 ohm load. And then that time varying magnetic flux induces an EMF in that loop formed by the center conductor feed through and the fixture base. Now, a couple of nuances here. These are some of these nuances that I mentioned at the outset here. Your measurement device is only reading half of the injected potential, half of the injected EMF. Okay, you're reading across one of these 50 ohm resistors. The other one is your dummy load. You're not reading this potential. You're only reading what's coming out this end. So the calibration potential your measurement device is reading is half of the injected EMF. It's sort of seems obvious, but you always have to keep that in mind, because I've done it myself where I'll do some calculation or look at some measured value and hey, this is a factor 2 off from what it should be, and then you realize, oh no, it really is, it's exactly what it should be. I just forgot the factor of 2. Okay. So the device is generally measuring in terms of voltage, or maybe in terms of power if it's dBm, but whatever the case may be, the injected current is flowing in a loop. Okay, so these 50 ohm resistors are really, you need to think of them as being in series, because they are. And so the calibration current is the calibration potential divided by the 50 ohm input impedance of the measurement device. Or the other way to think of it is that it's the injected potential, the injected EMF, divided by 100 ohms. Clearly, it's the same thing, but depending on how you're looking at it, you know, one of these might make more sense than the other, but they are of course equivalent. Okay. So when we look at our pre-calibration current, well, we went through the previous analysis of what the induced potential is from an incident field, you know, where we had this envelope here, and at above for L greater than lambda over 2, our induced potential is 150 millivolts per volt per meter. But we want to put this in terms of current. This, you know, magnetic flux induces a potential, but the test method, the CS114 test method, puts things in terms of a pre-calibrated current. So there we are. So we need to make that translation. So it's very simple. We're going into a 100 ohm calibration fixture. So we just take that desired potential, and remember this potential here is the total EMF, not the calibration potential, but the injected potential we had been talking about before is the total induced EMF. So we want to divide that by 100 ohms. Okay, so in dB space, that means subtracting 40 dB ohms. So the current transfer function in the high frequency plateau, well, that's our 150 volts per meter, 150 millivolts per volt per meter divided by 100 ohms. That's our 1.5 milliamps per volt per meter specified in the mill standard. That's where this comes from. So again, all the pieces fit together as they must. And then in dB space, it's 64 dB microamps per volt per meter. But this 1.5 milliamps per volt per meter is an important thing to bear in mind, because this comes up all the time. Okay. So okay. This is what we have in the calibration fixture. So now we're injecting into a cable under test. We're generally not all the time, but mostly what we are concerned about are shielded cables in an integrated configuration. Notable exception is power cables, but we'll set that aside for the moment. But if we're looking at a shielded cable that's terminated to chassis at both ends, from a low frequency standpoint, that's basically injecting into a short circuit. Now the inductance of the configuration comes into play, and that will affect what the impedance looks like at higher frequencies. But basically, you know, the extreme case is that you're injecting into a short circuit instead of the 100 ohm fixture. So you want to limit how much current you can inject into a short circuit. That's the maximum you're going to get. So mill standard 461F, again, doing this on purpose for the sake of comparison, and I'll just read this. Requirements are also met if the EUT is not susceptible at forward power levels sensed by the directional coupler that are below those determined during calibration, provided that the actual current induced in the cable is 6 dB or greater than the calibration limit. I'm not really thrilled with that wording, but there it is. That's what's in the mill standard. But the basic idea is that your maximum injected current per 461F is what's shown in the baby blue curve there. It's the entire pre-calibration curve shifted up by 6 dB. Okay, that's what that wording means. That is the intent of what that wording in 461F means. That is not what we're doing. Okay, mill standard 461G went back to the original specification when this test method was introduced in 461D in 1993. And here I'll just read this. Requirements are also met if the EUT is not susceptible at forward power levels sensed by the directional coupler that are below those determined during calibration, provided that the actual current induced in the cable under test is 6 dB higher than the level in the plateau portion of the curve over the entire frequency range, which provides better correlation to field to wire coupling behavior. So it's the flat level here across the whole frequency range. So it's 6 dB higher than the plateau level, but all across the frequency range. So mill standard 461G is the desired method because it provides better correlation to field to wire coupling behavior. As we went through earlier, we expect basically a flat inject a flat induced current into a low impedance for a given for a flat induced field, or flat incident field will induce a flat current over frequency. Because remember, you're calibrating into a 100 ohm controlled calibration fixture, but then you're injecting into something that is not going to be 100 ohms. So this is one case where the version of the mill standard you're calling out makes a tremendous difference. For a lot of things, if people say they're doing things per mill standard 461F versus G, say CS114, that's pretty much identical. That doesn't matter too much. Here, if somebody says they're doing CS114 per mill standard 461F, that is not what we want to do. We want to insist that it is per G, because this is the proper way to do it. This is the way it was originally specified, and then they went to this approach in E and F. But then when they released G, they said, no, this is what we want. We really should never have gone to this in E and F. All this to underscore why you owe it to yourself to know what the contents of the most current version of any document that you're using is, right? That when I hear people say, well, we're under contract for mill standard 461E or 461F, this is one of the prime examples that I bring up to show that is not a desirable approach, right? You need to be aware of why they've updated these documents, and in a case like this, to get back to doing the test properly. And then this is wording in the appendix that just underscores that. Instead of leveling primarily on the cable induced current, the pre-calibrated forward power is the primary target, with only a frequency independent induced cable current limit equal to 6 dB above the flat maximum portion of the applicable limit. Okay. Now, power cables tend to not be shielded, so at least at low frequencies, they will present a high impedance. So you will hit that pre-calibrated power limit at low frequencies anyway. At higher frequencies, the impedance is going to change over frequency, and you'll hit resonances and so forth. But anyway, the pre-calibration step is setting both the open circuit potential, or the pre-calibrated power limit, but it's effectively setting a maximum open circuit potential and the short circuit current. Okay. Now let's look at some subtleties of this pre-calibration step. This is an equivalent circuit here. The injection probe is functioning as a transformer. The primary is the coil of wire that wraps around the magnetic core of the probe. The secondary is your cable under test. The loop formed by the cable under test and the ground plane. Now in this case, while you're still in the calibration fixture, it's the center conductor of the calibration fixture going through the pair of 50 ohm resistors. So I've just shown those in series here. You have the 50 ohm dummy load up here, and then your calibration potential is what your measurement device is reading across its 50 ohm input impedance. Okay, so now the injection probe itself will have this, what we call a magnetizing inductance, that you can just represent it as an inductance in parallel with an ideal lossless transformer, right? So it's got some magnetizing inductance in parallel with the winding. Now, to really understand how all the nuances here of the pre-calibration and the whole injection technique, we have to start with the what I'm calling the generator potential, V sub G. This is what's upstream of the signal source's 50 ohm source impedance. Okay, so in any 50 ohm system, your signal source, an RF signal generator with a 50 ohm source impedance, when it tells you what your VO is, what your output potential is, it's assuming that you're hanging a 50 ohm load out here, okay? So the VG potential upstream of the 50 ohm source impedance must be twice what it is telling you VO is. And I'm putting VO in quotes because the whole point of this exercise is that if you don't put 50 ohms out here, then what the equipment is telling you VO isn't really what's there. So VO is in quotes here. This is the advertised or the displayed level at the output, and that's only true if you've got a 50 ohm load out here. If you connect this to a 50 ohm load, okay. So VG, the upstream potential is twice VO in quotes, or in dB space, it's 6 dB higher than what they're telling you VO is in dB microvolts. You can also do it in dBm, which is kind of the default. So VO is assuming a 50 ohm load, but the calibration fixture is presenting a 100 ohm load. So things are a little bit different. So we have to look at what is this VG potential, not VO, because this isn't really what's there. It's going to be some variation on that. Okay. Everybody clear on that? That's a really, really central point. And it's weird, and it's nothing anybody ever explained to me, really. I mean, I got some explanations and then reasoned it out for myself. So it can be a very weird thing to understand. Is everybody clear? Okay, well, I'll take that as a yes. So again, your calibration potential out here is half of the injected EMF, right? This EMF is what's injected, what your probe is injecting into that loop. Your measurement device is measuring half of that. Or again, in dB space, your calibration potential is the EMF minus 6 dB. And then your calibration current, and this again reiterating from before, is that calibration potential divided by 50 ohms, or your VMF divided by 100 ohms. And the same thing. Okay. So we look at insertion loss. Insertion loss is defined, again, I think in a rather strange way, but here we go to make sense out of it. I mean, this is how they tell you to measure insertion loss in the mill standard, that you apply a signal from your signal generator and go through the injection probe and then measure what is coming out into your spectrum analyzer or any measurement device here. And so the insertion loss in dB is defined as the displayed V out setting minus what you measure here, what you measure at the spectrum analyzer. So again, the V out level is not really V out if you're not putting 50 ohms out here. You're putting 100 ohms, and then at low frequencies, it's something different because of the magnetizing inductance. So at low frequencies, when your inductive reactance is much less than 50 ohms, and we're just going to assume the turns ratio. Some of these injection probes may have multiple turns around them. Most of the probes, I think all of the probes I have personally used have a single turn. But in the general case, they may have multiple turns and they'll function as an N-to-1 transformer, right? But for this discussion, I'm just going to assume a single turn. For low frequencies, when that magnetizing inductance, when that inductive reactance is much less than 50 ohms, then the VCal, well, first we'll just look at the EMF is going to be the voltage divider formed by the inductive reactance with the 50 ohm source impedance. That's what you have here, multiplied by VG, again, VG, not VO. And for VCal, it's half of the VEMF. So that's our factor of 1/2 out here. Okay. But the point here is that at low frequencies, the insertion loss is dominated by that magnetizing inductance. So far, so good. So the insertion loss is dominated by the physical loss of the probe in the form of this magnetizing inductance. Now at high frequencies, when the inductive reactance is much greater than 50 ohms, where you can basically take it out of the circuit, and we assume no physical probe loss, then my apologies, I kind of skipped a step here, that the induced EMF now is going to be yeah, I'm gonna have to go back, and I meant to fix this, and my apologies, I didn't do this. I skipped a step and went to directly to dB space. The equivalent circuit here at high frequencies, when the magnetizing inductance is a very high impedance and there's no probe loss, if this is a perfect transformer, then basically what you have is VG going through this 50 ohm resistor and then two more 50 ohm resistors. So the VCal should be 1/3 of VG. Everybody see that? Okay, so you have three 50 ohm resistors in series and you're tapping off only one of them. So it's just a simple resistive divider. So, excuse me. So 1/3 is, well, we a lot of times we round a factor of 3 up to 10 dB, you know, and in most cases that's close enough for what we do. But 1/3, a factor of 3 is actually about 9.5 dB. So when in numeric space where VCal is 1/3 of VG, in dB space it's the same as saying VG in dB microvolts minus 9.5 dB. That's all. That's what this is. So again, I apologize for skipping a step, but that's where this comes from. Everybody clear on that? Okay, so if we relate that back to VO, the way insertion loss is defined, well, VO is VG minus 6 dB. So this just means that VCal in dB microvolts is the displayed value of VO minus 3.5 dB. So that means that the minimum insertion loss, the way it's defined here, even if there's no physical loss in the probe, is 3.5 dB. It's just an artifact of the way they define how you make this measurement. That even if there's no physical loss in the injection probe, the best you can get is 3.5 dB. And so 4 to 7 dB is typical for these injection probes. Okay, everybody clear on this? It may seem like it's down in the weeds, but if you spend any time doing CS114 and looking at these insertion loss curves, it can be a little bit of a weird thing until you actually kind of think through what it means. So this is the verbiage from the mill standard. It says here, I'll just read this here. A control on insertion loss has been found to be necessary to obtain consistency in test results. Insertion loss is measured as shown, and that's the figure on the previous page. It is the difference in dB of the power applied to the probe installed on the calibration fixture and the power level detected by the measurement receiver. Now that's with the clarification of this point here. It's not really the power applied to the probe. It's what the signal generator thinks that it would be applying into a 50 ohm load. Okay. But just note that at low frequencies, we start at 10 kilohertz. So basically these curves are only meaningful above here at 10 kilohertz. But there's, you know, tens of dB of insertion loss, and this is this part of the curve is where the insertion loss is dominated by the actual probe loss. So the probe is going to give you tens of dB of loss at 10 kilohertz, and then the knee in the curve is about 1 megahertz, and that's actually about where the knee in the curve for the limit lines is. Coincidence? I don't think so, but we'll come back to that point. All right, so we'll look at a Thevenin equivalent circuit here. The Thevenin equivalent circuits are a really wonderful tool that I think they get forgotten by a lot of us, but when you do this kind of thing, in EMC they come in handy all the time. And I'm going to show you right now where it comes in handy. If we take this we're still looking at pre-calibration here, right? But if we look at this point right here, our injected EMF coming out of our injection probe, right? So we take a look at that point there, and we want to express what everything to the left of this point here, where we have our VEMF, we can express it in terms of an open circuit potential and a source impedance. And remember how you do that. You basically just you pretend this is an open circuit, right? You just open circuit your load, and what is the potential you're going to see looking back in this direction? Well, it's going to be formed by the voltage divider. You're going to have your VG through the impedance divider between the 50 ohms and the magnetizing inductive reactance, right? So again, you have this equation that may look like a mess at first, but that's all it is. It's just the impedance divider between the 50 ohms and the magnetizing inductance. And we've got our turns ratio here, which is most of the time is 1, but keeping it generic, I'm leaving the factor of n in there. So that's your open circuit drive potential. This is the maximum potential by definition that you will get into an open circuit. Then our source impedance, looking back in this direction, you short out any voltage sources and you open any current sources. And then what's the impedance that you see? We have no current sources. So we just short out this voltage source and you're left with the 50 ohms in parallel with the magnetizing inductive reactance. So that's your source impedance. Okay, so what do we do with all that? Well, the short circuit current is a direct function of those two things, right? When you go to inject into a cable under test and it looks like a short circuit, then that current that you're going to get is going to be that open circuit potential divided by the source impedance. Well, so this kind of looks like a mess, right? But looky here, all these frequency dependent terms cancel, and you're left with this, what I think is a very beautiful expression that tells you that the short circuit current is a constant value for a constant generator setting over frequency. And again, with the turns ratio here, but n equals 1 typically, and certainly I'm pretty sure for the probe I'm going to show you on Wednesday. So basically you can set your signal generator setting, and remember VG is the advertised setting plus 6 dB. But to get the desired short circuit current, a constant short circuit current over frequency, which is what we want, we can just set a constant signal generator setting, and our current is just going to be, well, the setting plus 6 dB divided by 50 ohms. That will give us our constant short circuit current over frequency. I think that's a really cool result, and that's what enables us to implement a simplified approach that I will show you on Wednesday. Okay, so this gets to our comparison of CS114 limits with RS103 limits. Each one of these curves, the default curves in the mill standard, is specifically defined to correlate to a given RS103 limit. Okay. Now the top one, curve number 5, corresponds to a limit of 200 volts per meter. So that's a very significant electric field. But that's at 110 dB microamps, so that's 300 milliamps, right? 1.5 milliamps per volt per meter. And so the lowest one in the mill standard, curve number 1, corresponds to 5 volts per meter. So we just take for our default applications for on-orbit applications, we basically just have defined a curve that corresponds to a level of 2 volts per meter. And RF transmitters are generally not used below 200 megahertz on spacecraft, so this is generally quite sufficient for controlling crosstalk. Okay, so so we are using it to control against crosstalk, but just defining the default limit to correspond to our on-orbit limit of 2 volts per meter just seemed like a good benchmark, right? And so that's 3 milliamps in this high frequency range here, and that's an easy level I mean, it's an easy level to achieve and also you can do it without an amplifier, as I'm going to show you on Wednesday. And, you know, if you're sensitive to 3 milliamps, you probably want to know about it. Okay. And so our default level in GEVs, and that we apply on most of our programs, unless we need something different, is the pre-calibrated level with 70 dB microamps in the plateau. So remember, well, yeah, okay, so 70 is what's here. In the earlier curve, it was 64 dB microamps, but that was per volt per meter. Okay, that was the normalized or the generic curve normalized, you know, per volt per meter. So for 2 volts per meter, we shift the curve up by 6 dB. Okay, so our plateau is 70 dB microamps, and it increases linearly from 10 kilohertz up to 1 megahertz. So note the knee in these curves is also right around 1 megahertz. So and that happens to be that is about where the knee in the curve of those insertion loss figures. You know, that's about the same as where the knee in the curve here for the insertion loss of your typical probes. In fact, to use a probe for CS114, it is supposed to fall in this range here. So that all just kind of falls into place. That using this approach, basically the characteristic of the insertion loss of the injection probe basically gives you this profile here. Gives you this injected potential into a 100 ohm load that will basically look like this. Okay. And then the maximum current per mil standard 461G is going to be, you know, into a short circuit is going to be 6 dB higher than the plateau level all the way across the frequency range. Okay, any questions on this? Because I'm going to shift gears and talk about power lead injection now. Okay, so remember that we also have to be concerned about establishing compatibility with the power system. So you know, we want to inject some controlled signal onto our primary power leads to evaluate conducted susceptibility. So we had CS101 to get the lower frequency portion. But in addition to testing for common mode conducted susceptibility, CS114 is also used for primary power lead injection from 150 kilohertz to 50 megahertz. So by comparison, the CS101 method, you know, we use the injection transformer that is physically connected in series with the power feed. The old CS02 method, for reference and comparison only, I really don't recommend anybody continue to use this. I think space station still continues to require this method, but I just mentioned this for comparison that and you know, we did use this method for many years. So instead of an injection transformer, there was this RF coupler that is actually about physical size here. You can hold it in your hand, but you take a signal generator, go through a power amplifier, and go through this coupler. It was essentially a capacitive coupling network. There's a little bit more to it than that, but you know, it's a high pass filter. And then it would give you, here's your detector output. This is what you would take to an RF voltmeter or scope or whatever. But it was a line to ground injection. You know, it wasn't line to line. You would actually connect the ground terminal to the ground plane. Okay. But you would inject the signal through this capacitive coupling network. And there are a couple of nuances about this test method. One, you needed a special breakout cable to inject less than 5 centimeters from the UT. The default CS02 by default went up to 400 megahertz. So you needed to be within 5 centimeters to be less than a tenth of a wavelength at 400 megahertz. Okay, and sometimes people didn't do that, and they would inject back here by the capacitor network 2 meters away, and you had no idea what you were actually injecting into the EUT. So for these higher frequency test methods, the location of your injection point is very important. It's not an arbitrary thing. The other thing is you're trying to inject the signal here, right? But then you've got this capacitor network to decouple from your power source to actually be able to get your desired injected potential here. Okay, so it was two things requiring a configuration change specific to this test. You needed a cable, a breakout cable that you needed to put in place to be able to inject your signal the desired location, and you also needed this 20 microhenry inductor to hook in series with the power feed. So here are the default limits for CS02 for mil standard 461C. This test method was not carried forward in mil standard 461D in 1993. So that tells you something. And I mean, and you can just see the typeface here. You can tell this is from an old document, but the voltage limit was 1 volt RMS from a 50 ohm source. And there was a pre-calibrated power limit, 1 watt into a 50 ohm load. So let's look at that. If you look at pre-calibration here, the 1 watt limit, basically that converted to a calibration potential of 7 volts, 7.07 volts RMS across that 50 ohm calibration resistance. So that meant that your open circuit potential, your drive potential upstream of its 50 ohm source impedance had to be double that, so 14 volts RMS. And then your calibration current was just over 140 milliamps RMS. So now you go to inject into the unit under test with whatever its load impedance is, which is frequency dependent, right? But you're going through your coupler here, which I'm just representing as an AC coupling capacitor. Well, remember, you need this 20 microhenry inductor to decouple you from the power source. Well, that also presents a load, right? The inductive reactance of this thing at 50 kilohertz, because the default for CS02 was that it started at 50 kilohertz. Okay. CS01 went up to 50 kilohertz and CS02 took over from there, and then the CS101 is extended up to 150 kilohertz. So just keeping those numbers consistent. But at the low end here, at the low end of CS02, just doing J omega L for 20 microhenries, that's an inductive reactance of about 6 ohms. Okay, well that's going to load down that drive circuit at low frequencies. You know, if at low frequencies where your input impedance of your device under test may be fairly high, this is going to be a dominant path. A lot of load current's going to flow in here, and it's going to affect the injected potential. So you needed that higher drive level to compensate for that at the low frequencies. But then, you know, it's just kept at that same level, the 1 watt across the whole frequency range. So even as the frequency goes up and then the impedance of this inductor goes up and doesn't load things down as much, you still at least have the capability, the capacity to drive 14 volts of open circuit potential here. And so if you put a short out here, that's where that comes into play. I mean, your control loop is going to when the control loop is working, right? It's going to limit you to 1 volt here, right? But if you've got a low impedance, then that's when it's going to keep increasing the drive level until it just hits that limit of 14 volts, right? But if you have a short circuit out here, that means you can have a short circuit current of just over 280 milliamps. That's a lot of current. That is a lot of current to drive into some flight hardware. So there are a lot of reasons why I don't like CS02, and I really don't want anybody to continue using it. If you're doing a space station payload and you know the ISS documents specify CS02, well, then there you go. That's what you got to use. But if you've got a choice in the matter, please don't use CS02. Use CS114. we can use that for power lead injection, right? As we've just gone through here, we can inject a potential on a power lead just as well as we can inject it onto a bulk cable for common mode. And 400 megahertz is totally overkill for controlling conducted susceptibility on power leads. We only control conducted emissions up to 50 megahertz. So there's no particular reason to do CS above 50 megahertz. Because at high frequencies, your input filters pretty much squelch anything. So we've generally found over the years 50 megahertz is a more than sufficient upper frequency for testing conducted emissions and susceptibility. So one thing that works in our favor here is limiting the upper frequency to 50 megahertz. Well, the wavelength at 50 megahertz is 6 meters. A tenth of a wavelength is 60 centimeters. So we can relax the placement of our monitor probe and our injection probe to 30 centimeters from the monitor probe to the EUT, and then another 30 centimeters to the injection probe. Now that's less than or equal to. It doesn't mean you have to go to 30 centimeters. And if you can get them right up against the EUT, so much the better. But this just relaxes that placement to get the whole ensemble to within a tenth of a wavelength of the EUT at the highest frequency of interest. So there's no special breakout cable needed. You just clamp the probes around the power lead, and it requires no disconnections, and it's simpler and much more efficient to use than CSO2. CSO2 required a configuration break. If you're testing multiple power feeds, I've seen this happen. You're testing multiple power feeds on a given EUT. You got not only reconfiguration but a power cycle, right? If you're messing with those connections on each power feed, right? You got to turn off the power unless you've got enough inductors, to just have everything set up. But you cycle power, move everything over, and then power up again. And on some of these EUTs where the power cycling time is significant, half an hour to an hour, that adds up and that eats up test time. And if you use CS114, you don't have to do any of that, and you can just bang out your CS testing on these cables one after another without power cycling, without any disconnections. And the default voltage limit of 1 volt RMS equates to 10 milliamps RMS or 80 dB microamps into the 100 ohm calibration fixture. Now, automated CS114 test systems generally work in terms of current. And that's by default what you're monitoring when you're injecting into the EUT. So I've seen in some places where people will specify a voltage limit and monitor the voltage here into the EUT. There you are back into the realm of needing a special breakout cable to be able to monitor the voltage there. If you do your pre-calibration to the 1 volt RMS, then that's the maximum potential that you're going to inject, and then you monitor the current, just to keep tabs on what's the maximum current that you could be injecting when you go to a low impedance. And so your maximum injected current here then is 6 dB above the pre-calibration level. So 86 dB microamps or 20 milliamps. That's a whole lot less than 282 milliamps that you could inject with CSO2. So I like this a lot better. Then here is where we get into the simplified setup, and this is what I'm going to show you Wednesday. So I'm just going to say a few words about this to give you a sneak preview, and then I think we'll call it good for this session and just open it up for any questions. But forget that you saw that picture on the right for just a moment. This is the full setup, the full CS114 setup per the mill standard. So you have, I'll just walk through some of the equipment here. So so the top is your power input. So this is when you're injecting into power lead. So for common mode, things are down here, your interconnecting cables. So here's your injection probe. That's kind of the center point. so here's your monitor probe. You're going into a measurement receiver to monitor in real time what is the current that's going in or being injected on that cable. And so from your injection probe, you need a signal generator, and for higher levels, you would need to go through an amplifier. And so the full setup tells you go through this directional coupler, and then take your measurement receiver is connected to the directional coupler. Now, when I took a course on, well, a full day course, multiple day course on mil standard 461 testing a number of years ago, one of the things that was pointed out, I mean, this is a more complicated setup, but one of the things this allows you to do, for whatever it's worth, if you ever encounter this, if your signal generator or even your amplifier crap out after you've done your pre-calibration, and you have to replace it, you have to replace either one of them when you're injecting into your cable under test. Strictly speaking, you don't have to do the calibration again if what you calibrated against was a power reading out of your directional coupler. Now, I think if my amplifier or signal generator crapped out, I probably would want to do my pre-calibration again. But the instructor of that class did point out, if you're monitoring forward power out of this directional coupler, and then at some point you have to replace either one of these pieces of equipment, you know, what you're playing back are against your lookup table you've created of the forward power numbers as a function of frequency, and you don't necessarily have to repeat that calibration. Anyway, just throwing that out there, just something I learned many years ago. But this is a little bit of a complicated setup. It's not too bad, but once you get the hang of what all this equipment is doing, then it makes a fair amount of sense. But when you're dealing with lower signal levels, like we generally are for our common mode level of 3 milliamps of 70 dB microamps, we don't need an amplifier for that. So we can connect our signal generator directly up to our injection probe. Okay, and and one advantage to this is that the signal generator setting we need, as I'll show you on Wednesday, to get the 3 milliamps is generally about 108, 109 dB microvolts, so a little bit less than 300 millivolts, right? 120 dB microvolts is 1 volt RMS. And that's into a 50 ohm load. So the open circuit potential that these signal generators can provide, certainly the RF signal generators that I've been using, their maximum drive capability is 120 dB microvolts RMS, or 1 volt. And so the open circuit potential is twice that, or 2 volts RMS. So if you fat finger that and go to full scale while you're running a test, and you want, what you want is 108, 109 dB microvolts, but the maximum you can get is 120. You've only got about 10 or 11, 12 dB of headroom there. You're basically not going to damage anything if you go 10 dB above your intended test level. So it's a very safe, a much safer test setup compared to this setup where you've got a drive amplifier. What's not shown here is some of these automated test systems. I think the one we've been using here at Goddard, the amplifier is pretty hefty because they have to be able to drive those curves that are injecting much higher signal levels. The amplifier could be a couple hundred watts, and we don't need anywhere near that kind of power to drive the levels we want, at least for common mode. So you need to put some hefty attenuation in line with that. So when you've got an amplifier that's capable of driving that much power, there's, you know, in the worst case, you could end up applying that full amount of power to your test article, right? It's not the best idea to rely on a software control loop to limit the injected power. You want some hardware limit on the available power that you can inject. With any susceptibility method, there is always some tangible risk of damage, and you need to control that in as many ways as you can. So controlling the open circuit potential and the short circuit current are certainly important parts of that. But if there's only software control limiting those, software can fail. So if you use a signal generator that can only put out a volt, or worst case 2 volts into an open circuit, that's a really good safeguard, and it's a much simpler setup, right? You're just driving the signal generator, connecting that directly to the injection probe, and then it's optional. You can just play the pre-calibrated levels back, and the current is what it is. I always still like to monitor the current in real time, just to make sure that I'm getting that I am indeed injecting something, right? I don't worry too much about the specific current that's being injected, because that's going to be dependent on the impedance of the loop at any given frequency. But just verifying that you're getting some injected current just verifies, it tells you that your injection is working. You are injecting a signal and testing the EUT. And that's what I'll show you on Wednesday. So that's a good place to wrap this up. So does anybody have any questions or comments based on what we talked about here? No questions at all? Is anybody still there?
Oh yeah, right here.
Writing my notes.
Okay. Well, as always, feel free to email me if you have any questions, or if you'd like to talk about any of this separately, or But as I say, CS114 is a very nuanced test method, and it takes many iterations going through it to really understand those nuances, and I'm still learning new things about it every time I do it. But it is extremely useful, and I like I say, and when I show you how to run that simplified method on Wednesday, I hope it'll inspire you to actually run it on your hardware in your development lab before you ever come to the EMI lab, because it provides you very valuable information on how well built your cables are and stuff like that. It's a very, once you get the hang out of how to run it properly, it is a very quick and easy way to check how susceptible your cables are. And that's something that you want to know about, right? If you've got sensitive analog signals on a cable, you want to know how good is your shielding, how well protected is it, and the more tools that you have for evaluating these things early on, the better off you are, as opposed to just waiting until you come to the EMI lab. And an RF signal generator, I mean, I guess that can be kind of pricey, and those injection probes are $5,000 or $10,000. So for every single person in a development lab to own one of those, okay, that can get a little pricey. But you can always let us know you'd like to do a test like that, and we can certainly lend you the equipment or come over and help you run it. Because I mean, that's what we're here for, is to help you evaluate your hardware and determine if there are any improvements you need to make to it to make it more EMI robust. So going once, any questions, comments? Going twice? Okay, going thrice. Thank you all very much for participating, and look forward to talking to you on Wednesday when we're playing in the lab.
Thanks, John.
Okay, thank you.
Cheers, John.
Thank you.